1, then essentially the graph you have is a tree. And a tree-shaped constraint graph essentially can be solved with just arc consistency. Tree-shaped constraint graph means it has induced width 1. That means if you do directional arc consistency, which is k equals 1 plus 1, 2, then it's then you can do it, solve the problem without backing. Okay. The only difference what we discussed here up to here is just the width, and induced width is the same notion, except with respect to the ordering, you will put induced edges between parents of any given node. So if the parents, so for example, you put a edge between B and C, because let's see, B and C will wind up being parents of the node. So the reason you need to find a node for which B and C here. Sorry. D winds up having edge from both B and C. D has an edge from both B and C. So this is the family values idea, right? This is also actually called, in another context, it's called moralizing a graph. So if you have two parents, they should be married, right? And the induced edge, so if they were not married up front, you put an induced edge saying they are married. Okay, that's what the inducement is. Okay, so moralizing the graph. So for every pair of parents of any node, according to that ordering, you put an induced edge. And then after doing that, you still define the tree width, just the same way before. And all that you really care about is induced width. If the graph has induced width k, then directional k consistency. I'm sorry, directional k plus 1 consistency. Ensures backtrack research. Okay. The only notion, of course, the only thing that you have to realize is induced width is a non-trivial property. It's not like you pick an ordering and see width with respect to that. For every ordering, there is an induced width. And you consider the minimum induced width over all orderings. So now the question is, how hard is it to compute the induced width? Because there are n factorial orderings, or an n vertex graph, and you have to consider induced width for all of them and take the minimum over them. Turns out, in the worst case, it is indeed exponential. In fact, induced width computation is an NP complete problem. However, there are greedy algorithms that will give you reasonable approximations. Okay, reasonable approximations means if the induced width of a tree is 3, and you more likely that you'll only approximate it as 4 or 5 or 6, so you will wind up overestimating the width. Do you see what I'm saying? Because if you saw more, because you're always taking min over, suppose instead of n factorial, you took just 5 orderings, okay, and just took the minimum over those 5. That is guaranteed to be higher than the true minimum width, just by definition. Okay, so greedy algorithms are there which will give you induced width, a good approximation to induced width, which will still be an upper bound. And that will tell you upfront, beforehand, before you even started solving the problem, how hard the problem is. Okay, if the upper bound on the induced width is k, then the upper bound on the consistency enforcement is k plus 1. and it will become polynomial after that. That's a structural property. That's very useful. And that's the build-up for why we needed to understand consistency and directional consistency enforcement. Because essentially it's connected to the notion of, once you have the induced width k, then what you need to enforce is that induced width k is with respect to a particular ordering, right? And so you pick that ordering, and with respect to that ordering, you enforce k plus 1 directional consistency. This is only useful theoretically. Nobody actually does this in practice, right? It's useful theoretically to say that certain classes of problems are really polynomial, even before you solve them. Okay? If in fact you're trying to find the induced width up front, which is an NP-complete problem, and then find the directional consistency enforced by that induced width, that will be another extra, n power k plus 1. And then you do search. More often than not, you would have done more work than your friend who just jumped in and did variable ordering, most constrained variable, least constrained value, and forward checking. It's just from theoretical point of view, it's a very useful idea. Okay. Next time, I will take care of the mess I created on the directional consistency example, and also we'll talk about the compilation of planning problems into SAT and space.